Greetings. The same few questions have been asked by several folks regarding the theory of positivity video and the theory of static energy video. Hopefully this video will answer all those questions. There are also a couple new designs just for fun. I was also bawled out by an expert who claimed I do not understand what he did not even bother to contemplate. So for all you experts out there, I will begin this with a few sentences regarding Joseph Newman and Thomas Townsend Brown. For the rest of you, please bear with this. It will only take a couple minutes. So experts, imagine if you will a semi-superconducting coil of wire the size of a house, millions of turns of very low resistance wire, insulated as thin and as strong as possible. This coil will take a relatively long amount of time to react. You hit that coil with 10,000 volts of very stiff voltage from an appropriately sized battery bank, just long enough for that coil to become magnetized. At that point in time, the battery bank has used very little energy to magnetize the giant coil. It has mostly just maintained 10,000 volts while the coil reacted. So you instantly remove the battery from the coil at the precise instant that the coil begins allowing amps to flow, and you harvest all the back energy, including the huge spark and including the heat generated by the imploding coil. The back energy will be hundreds, if not thousands of times greater than the small amount of energy inputted into the coil from the battery bank. The back energy will not be lower volts and higher amps. It will be higher volts and higher amps. If this is not plainly obvious to you, then you are certainly not an expert in this field. Or we know from T. Townsend Brown that very high voltage can also produce very high thrust under specific conditions. We also know that voltage alone requires little energy to maintain, so that very high thrust can be produced with very low energy. Lockheed Martin et al. Have already done this to death, and by now they are light years ahead of Brown in their technology. Literally. So put a couple of evolved T. Townsend Brown thrusters on a wheel, and you have much more energy out than in, obviously. Okay, enough of that. So for all you non-experts, the only folks who seem to be interested in this, here are hopefully a few clarifications that will answer your questions. There is some repetition with the other videos necessary for the sake of consistency of this video. So this represents a table with a rocket ship on one side and a bowling ball on the other side. The rocket ship is producing 15 pounds of force, pushing down on the table. The bowling ball weighs 15 pounds and is therefore doing the same. The difference, of course, is that the rocket ship continues to burn poisonous fuel in order to produce that force, whilst the bowling ball burns none at all. Is there any possible way in the entire universe of possibilities to take advantage of the fact that gravity will produce force forever, free of charge, without burning any fuel to create kinetic energy? Yes, there is, grasshopper. Our universe does it continuously by mating gravity with inertia under very specific circumstances, or voltage with reactance, etc., etc. So what is inertia? We'll explore it with a few thought experiments. Einstein did these all the time, no need to be embarrassed. So this is a dude pushing on a perfectly round solid steel ball, which is resting on a perfectly flat and level steel floor. Because the ball is so massive, it will take that dude a lot of energy just to get it rolling. But once it is rolling along, if he runs out in front of it and tries to stop it, it will take just as much work to stop it as it did to get it going in the first place. If he tries to stop it with one of his feet, it will crush his little toesies. That's inertia. A bigger, more massive ball would take even more work to move, but then once it was moving, it would take just as much more work to stop it from moving. Gotta love my artwork. You see this little dude here? That's a little guy pushing on a stick, pushing on a huge steel ball, rolling along a flat and level steel floor. And we're imagining everything is so perfect that there's not dimpling the floor or anything like that. So energy in and energy out are always equal when it comes to pure inertia. The amount of energy needed to stop one of these balls from rolling will be equal to the amount of energy used to get it rolling in the first place, minus friction, blah, blah, blah. Here's the important part of all this. This inertia thing is just as true for a ball of steel floating out in space as it is for one resting on a flat steel floor. We will assume this dude and this massive steel ball are both floating weightlessly out in space, far removed from all other physical things. If this guy balls up his fist and hits this solid steel sphere as hard as he can, it will not take off immediately at the speed of his fist. It will just sit there and he will break his knuckles. Then he will notice the ball slowly floating away from him. Why? The big mass of steel has inertia, even if it doesn't have weight. On 5 different sized planets, it will have 5 different weights, but its inertia will always be the same. It will take energy to get this mass of steel moving, but then once it is moving, it will take the same amount of energy to stop it from moving that was used to cause it to move in the first place. That's inertia. This represents 3 identical rocket ships pushing on 3 different steel balls. We will stipulate that these 3 rockets are completely alone in space, millions of miles from each other and trillions of miles from anything else. There is no gravity or anything else affecting these in any way whatsoever. These rockets burn exactly the same amount of fuel at exactly the same rate. They are the same size, etc., etc., completely identical in all respects. 1, 2, 3. However, they are pushing 3 very different sized steel balls through space. The small one weighs only a few pounds, the middle one weighs a few billion pounds, and the large one weighs a few trillion pounds. That is how much they would weigh here on Earth. They don't weigh anything out in space, but they still have their own inherent inertia. So, each rocket will produce exactly 10 pounds of force for 1 hour and then run out of fuel. All 3 start at exactly the same time and all begin pushing on their respective steel balls. The rocket attached to the smallest ball will take off immediately and shoot out into space very quickly, continually increasing its velocity for the entire hour. The rocket attached to the mid-sized ball will take off more slowly than the smallest, but more quickly than the largest. It will also continue to increase in velocity during the entire hour, but at a slower rate than the smallest and a faster rate than the largest. And the rocket attached to the largest steel sphere will take off very slowly because the ball is so massive, because it has so much inertia. It will also continue to increase in velocity for the entire hour, but that increase will happen at a much slower rate because the massive steel ball has so much inertia. Here is the biggest steel sphere of them all. It is so big that the rocket would look like a dot on the side if this drawing was to scale. It's as big as the moon, whatever. It's imaginary. Again, we are stipulating that this is alone in space, far removed from all other things that might interfere with its motion. In this case, it takes the full hour just to move this thing 1 foot. Here's the thing. At the end of that hour, this huge ball moving at 1 foot per hour has the same amount of energy as the smallest ball moving at 1 million miles per hour. In other words, it would take the same total amount of energy to stop this huge one from moving as it would to stop the smaller one from moving. there would be different methods needed to stop the big slow one, as opposed to the methods needed to stop the small fast one, but the total energy needed would be the same for each. Now, in these 4 cases, no extra free new energy has been created because the force of the rockets was produced by burning fuel. In this case, the inertia of the fuel molecules creating pressure against the hull of the rocket ships was simply transferred, as it were, into the inertia of the steel balls. Inertia versus inertia cannot create energy. 2 fathers together cannot make a baby. So how does energy get created in the first place? Dad and mom, inertia and gravity, voltage and reactance, etc., etc. Another thought experiment just to get the point across. So this represents our huge steel ball right there, the one that only moved 1 foot in 1 hour, attached to a very long cable. Where am I? I can't point and read at the same time. Several million miles long, which has a 10-pound weight attached at the end. This cable would be much longer than this. I just drew it short to fit on this page. This is the surface of a planet, which is millions of times more massive than this thing. Okay. We will assume that the total force which is pulling down on our huge steel sphere is 10 pounds. This is accomplished by placing this huge ball far enough away from the planet so that the gravity of the planet is not pulling on it, but the cable extends down somewhat into the big planet's gravity, just far enough so that 10 pounds total, including the weight of the cable, is pulling on the big sphere. Most of the cable would be weightless. In this very imaginary case, the 10 pounds of force will pull on the huge ball for 1 hour, and the ball will move 1 foot closer to the planet during that hour. The gravity of the planet will produce the slow acceleration of that huge ball during the entire hour it accelerates, not any constantly burning fuel. So this is gravity interacting with inertia rather than inertia interacting with inertia. So this huge sphere at the end of the hour, moving at 1 foot per hour, has gained the same total amount of energy as a small ball in the previous examples, moving at 1 million miles per hour. So here is the trillion-dollar question. How much energy would it take to lift that 10-pound weight back up 1 foot to its original starting position? How much energy would it take you to lift a 10-pound bowling ball 1 foot? Very, very little. Did our huge steel sphere in space gain more energy than the minimum amount needed to lift 10 pounds 1 foot? Of course it did. It gained thousands of times more energy. Here is the point of all this. A large amount of inertia accelerated by a small amount of gravity over a long period of time through a short distance of space will gain new energy from that gravity under certain very specific conditions. And please keep in mind that all of these examples have atomic and electric allegories, which will be revealed in upcoming videos, if I'm allowed. So here we have 2 superconducting inertia generators. We won't worry about specifics. Those are in the first video. Both of these generators oppose the downward forces applied to their handles purely with inertia. So here's the handle, there's the force of the bowling ball pushing down on it. There's a handle, there's a rocket pushing down on it. They both start up here and slowly descend down to here. Start up here, slowly descend down to here. Okay, where am I? Both of these generators oppose the downward forces applied to their handles purely with inertia, and there is so much inertia that either the bowling ball pushing down on this handle from here to here, this handle from here to here, or the rocket which is producing the same amount of force as the ball, either one takes 10 minutes to descend from here to here. Where am I? Which we'll decide is 2 feet. 10 minutes to descend 2 feet, being opposed by only pure inertia. Where am I? So how much energy did the generator with the ball produce? Exactly the same amount as the one with the rocket, burning all that fuel for 10 minutes. Did both generators at the end of the 10 minutes gain more energy than the minimum necessary to lift that bowling ball back up to its starting position? Where'd I go? Did both generators at the end of the 10 minutes gain more energy than the minimum amount of energy that would be necessary to lift that bowling ball back up to its starting position? The answer is yes, absolutely. Now, did our universe gain any energy from the generator being powered by the rocket? No, of course not. Energy was simply transformed, as it were, from the rocket to the generator. Did our universe gain energy from the generator powered by the bowling ball? Yes, absolutely it did, if that energy was taken from the generator properly at the end of the cycle. In other words, if all that energy was taken from the generator immediately in the form of electricity, as soon as the ball descended from here to here. Now there's more about that in the other video. I don't want to be overly redundant. So energy simply is force plus time, regardless of how that force originates, right? Temporary poisonous fuel or eternal natural gravity. Both are energy. So this may be too small to read, especially you whippersnappers looking at your phone. So here we go. Energy is force plus time. Motion is mass plus space. Force plus time produces mass plus space. Mass plus space produces force plus time. In other words, energy produces motion, motion produces energy. There are two kinds of energy. Two kinds of motion. Relative motion associated with inertia. That's motion through space and time, what we're familiar with. There's also absolute motion, which is associated with gravity. And that is motion with space and time. Or it might be more precise to say space and time with that motion. That is motion in all directions simultaneously forever. In other words, the Earth, our motion here, is 32 feet per second in all directions simultaneously forever. We used to call that gravity. The proper way to understand that is motion. So everything that exists has two kinds of motion. The kind of motion we're used to thinking about, like the Earth spins and then it also orbits through space. But then there's also that's a relative motion. There's also the absolute motion, which is the 32 feet per second in all directions simultaneously forever. And everything that's physical has both those kinds of motions at all times. And there are likewise two kinds of energy. Relative energy associated with inertia. That's energy in the universe transferring mass to mass, the kind that we're used to. There is also absolute energy, which is associated with gravity. That is energy of the universe, infinite and eternal. And there is no loss of absolute energy when it mates with relative energy and increases that relative energy. No loss of absolute when increasing relative. Now, electricity involves both types simultaneously. And then inertia is the masculine aspect. Gravity is the feminine aspect. Our universe is a huge family of relationships. So we obviously cannot make a practical inertia generator using massive steel balls to provide that inertia. Is there any way to simulate this relationship using less mass, using less amount of stuff? Of course there is. So these, where's my pointer again? These things here represent scales which indicate how much weight is pressing on them, or how much measured weight is pressing on them. These are 10-pound bowling balls. These are long, thin aluminum planks, about 3 inches wide, that have depressions cut in here and here and here for the balls to rest in. The planks are attached to the floor. These are floors, and we're imagining these things are level, even though the picture doesn't look that way. These planks are attached to this floor. Where am I? Through these pivots. This is a pivot, which are attached to these bars, which are bolted into the floor. So without the bowling balls on them, these planks can swing up and down. Where am I here? Whoops. They can swing up and down like this. This is so high-tech, ain't it? From the pivot, so they are just resting on the scales. So the top drawing shows the balls directly on top of the scales, so the scales will each show 10 pounds plus the measured weight of the planks. In this center picture, the balls are further from the pivot, which is also the fulcrum of this lever. And hopefully it is obvious that the scales will measure much more weight because the weight of the balls is being amplified or magnified or increased, however you want to say it, by the leverage of this distance. And this bottom picture obviously shows the most weight being measured by the scales, increased by the leverage of this distance. So here we have simulated increasing weight without increasing mass. And what we gain in force, we lose in distance, blah, blah, blah. That's not the point. I'm just going to do that. Where the hell am I? So these are not the same as the previous. Notice there is only one scale in the center. Also that the 10-pound balls are resting on only one plank, which spans this entire length. The plank is very rigid and solid. In this case, the weight measured by the scale will not increase regardless of where the balls are resting on the plank. In this top picture, the scale will measure 20 pounds plus the weight of the plank. In this center picture, the scale will still measure 20 pounds plus the weight of the plank. You might have to think about that for a second. In the bottom picture, the scale will measure less than 20 pounds. So be clear about this before you move on. So keep in mind here in the center picture that the leverage on one side is being balanced or neutralized by the leverage on the opposite side. In this situation, the measured weight remains the same, different than this situation where the measured weight increases. Now let's decide that this point here is also an axis. Maybe there is a hole in the plank with a smaller diameter bolt through it from the top down, but not tightened down, so that this plank here, where am I, can freely spin parallel with the floor, like spin this way, parallel with the floor. In this case, the inertia of the spinning balls will be amplified through the leverage of this distance. This scale will see this weight exactly the same as it sees this weight in contrast to this. However, if we assume these balls are rigidly attached to this plank and we give it a good spin that way, parallel with the floor, then the inertia of those balls will be amplified through the leverage of this distance from the center. The force will be greatest at the center, just like a lever, and then decrease further from the center, just like a lever. And what we gain in force, we lose in distance, etc., etc. So here is the same situation without the scale. Now this is simply a spinning arm attached to an axle. Obviously, if this thing is spun, the inertia of these two weights on either end will be greatly amplified here in the center because of the leverage of this distance, just like a lever. So we have simulated increased inertia without increased mass. I'm just going to do it this way. So here we have a perfect flywheel made as perfect as money can buy, as perfect as modern technology can possibly produce. Perfectly balanced, perfectly round bearings and so on, and it is inside a plastic cube which has had all the air removed, so there is no air friction. It's perfect. It's 10 feet across, 10 feet. This outside is a donut-shaped ring of lead, and we'll say 6 inches in diameter. That's 6 inches in diameter through the round part of this. This inside aspect of the wheel is 1/4 inch thick cast aluminum, very light but very strong. So just like our arm in the previous drawing, most of the inertia will be along this outer edge. Obviously, if we give this a spin, the inertia of the outer lead ring will be amplified greatly, here in the center. The radius of this circle will act like a 5-foot lever, amplifying the inertia of the entire lead ring. So this is the same flywheel, but the base is not drawn in. We can assume it is there, we just didn't draw it in because it gets in the way. We will now compare how this perfect flywheel behaves with 8-ounce weights placed at different distances from the center. So first we attach our 8-ounce weight to the outer edge right here. That's what that thing is. Hope you can see that. And then let go of the wheel. The wheel will begin slowly to spin as the weight slowly descends. Then it will continue to increase in velocity as the weight falls toward the lowest point. When the weight has reached this lowest point, the wheel will be spinning at its fastest velocity in this situation, and the wheel will continue to spin because of the inertia of the lead ring. Once the weight has passed this lowest point and begins to ascend up this side, that weight will then oppose the spinning of the wheel, which will nonetheless continue to spin because of its inertia until the weight finally stops it from spinning. The weight will stop on this side, but just short of the height it began from on this side. It will stop short because of the minuscule amount of friction of the bearings against the axle and so on. We will decide it stops 1 inch shorter on this side than the height it began from on this side. Then the same thing will happen again. The weight will begin to descend, and it will slowly increase in velocity. It will pass this lowest point and then slowly ascend up the other side, stopping 1 inch or so short of the height it began from on this side. And the whole thing will continue to swing back and forth in slow motion like a giant inertia pendulum, losing 1 inch or so each cycle until it finally stops with the weight resting at the lowest point. Okay, next we will place the same weight right here, about 1/3 of the way toward the center, and then we will let it go. Everything will happen exactly like the first example, except it will all happen more slowly. The wheel will spin more slowly because the weight is closer to the center and therefore does not have as much leverage. When the weight reaches its lowest point, right about there, the wheel will be spinning more slowly than the first example, but it will continue to spin more slowly as the weight ascends up the other side. It will continue to spin because of the inertia of the lead donut. Sounds delicious. Even though it spins more slowly, the weight will still ascend until it reaches almost the height it began from. It will take more time for the weight to ascend from its lowest to its highest point because the wheel was moving slower with less energy than the first example. But now, because the weight is closer to the center, the wheel does not need to do as much work to lift it. Not only because there is less distance for this weight to travel from here to here compared to the previous weight, which had to travel all the way from here all the way up to there. Not only because of the difference in distance, but also because this weight is closer to the center, right there, it has less leverage than it did when it was furthest from the center, right here. And so right here, it is not opposing the inertia of the lead ring with as much force as it did when it was attached to this outer edge. Of course, outer edge, longer lever, more force. Closer to the center, shorter lever, less force, blah, blah, blah. But now we have a time paradox in that the wheel with less energy in the second example took more time to lift the weight. It kept the weight suspended as it continued to ascend for a longer period of time, but using less energy. And again, this is a thought experiment. We're assuming nearly perfect bearings and nearly eliminated friction and etc., etc. So, what did I do here? Okay, in this example, our 8-ounce weight is very close to the center, and we are still assuming perfect bearings, blah, blah, blah. So that the friction in the center is not a significant factor. I just said that. It's a thought experiment. We place the weight here on the wheel and let it go. The same thing will happen again, exactly as the other examples, back and forth like a slow motion inertia pendulum, except it will all happen very, very slowly. Okay. And the time paradox will increase in that, even with much less energy, the wheel will take a much longer amount of time to lift this weight, same 8-ounce weight, from its lowest to its highest point on the other side. Why is this significant? Because in this case, assuming the friction at the axle has been all but eliminated, the wheel has gained enough energy from the weight not only to lift it back nearly to its starting height, but also to keep it suspended in midair during the long amount of time it is being lifted. The wheel has gained energy. Yes, it has. The minimum energy that would be needed to lift the weight from its lowest point straight up to its original height, right? Not its original location, only its original height is important. The energy needed to do that is slightly less than the total energy used by the wheel to lift it from here up to here and to keep it suspended in midair during the time it ascended. Those two amounts of energy, the amount used to lift it up in combination with the amount used to keep it suspended during the time it ascends from here to here, that's what I wrote down. That total is how much energy the wheel gained from the weight. That total is more than the minimum needed to lift that weight back to its starting height. Okay, this is easier to understand using a comparison. Imagine lifting a 10-pound bowling ball up 1 foot. You grab it from a 3-foot high shelf and set it up on the shelf above, which is 4 feet high. You grab it, you lift it, set it on the higher shelf, no problem. Now imagine lifting it up very, very slowly. Lifting it the same 1 foot, but this over a period of 5 minutes. Everything the same, except you have to use your muscles to keep it suspended in midair for 5 minutes as you very slowly lift it from the 3-foot shelf to the 4-foot shelf. That took a lot more work to lift it the same distance over the longer period of time, right? Right. So now we begin to see how nature does things. This weight, being closer to the center, feels lighter to the inertia of the lead donut, just like it would feel lighter to you if this distance was a lever. But it is just as accurate to say that this inertia, being further from the center, feels like more inertia to this weight, just like it would feel like more inertia to you if you spun this wheel and then tried to stop it from spinning by putting your hand here instead of here. So then what does this condition simulate? A large amount of inertia accelerated by a small amount of gravity over a long period of time through a short distance of space. Where have we seen that before? So the three examples of this weight being placed in three different spots simulating equal forces opposing increasingly greater amounts of inertia. So from here, greater inertia, greatest inertia. That could be compared to our three rockets pushing on three increasingly massive steel spheres through space. But instead of rockets burning fuel, we used weights burning no fuel at all. But also notice, in these examples with the perfect flywheels, that the extra energy that has been gained by the wheel, oh, where's my pointer? When this weight has fallen to its lowest point, that extra energy is lost if the wheel is simply left to behave like a pendulum. The only way our universe would gain new energy from this situation is if the energy of the wheel was taken suddenly from the center in the form of electricity when the weight has reached its lowest level. That's a whole nother video. Whoops, they're right there. So, just for big fun and for super clarification, imagine this wheel is a mile across. It's a big damn wheel. It is still built as perfect as possible, perfectly balanced in all directions, perfectly round bearings. It's inside a huge cube with all the air removed, etc., etc., etc. It's perfect. The lead donut here is maybe 100 feet in diameter, and this weight is 280 feet from the center. Now I said that because these distances are actually to scale. Each cube's about 140 feet, assuming this is 1 mile long. So, 1 mile across, I should say. Where the hell am I? So the body of the wheel is as light but strong as possible, cast aluminum being thicker near the axle and thinner near the donut, etc., etc. We'll use a 1-ton weight to rotate the huge wheel. Now we are stipulating that the effect of this weight to rotate this wheel is at least 100 times greater than the effect of the friction on the axle to stop it from moving. It's a thought experiment. It could be done if we spent $1 billion doing this. It would be ridiculous. So after this weight is attached, it is released, and the wheel begins rotating very slowly and continues to increase in velocity as it rotates, but at a very slow rate, as the weight falls to its lowest point, which is right there. We will decide for the sake of simplicity that this takes 3 minutes. It will begin falling very slowly, then continue to slowly increase in velocity as it falls, but altogether it takes 3 minutes to descend from here to there. Once it reaches its lowest point, it takes slightly less than that, almost 3 minutes, to ascend to its highest point on this other side, almost as high as its original height. If there was no friction or imperfection at all, this would swing back and forth for years, but because of the friction on the axle and other imperfections, it will lose 1% or so of energy each cycle, if it is left as a pendulum. So the point of all this, hopefully, that is very obvious now, is that the wheel has gained enough energy once this 1-ton weight has descended to this point, not only to lift that 1-ton weight almost to its original height, but also to suspend that 1 ton in midair for almost 3 minutes while it is being lifted. And those two amounts together are greater than the minimum energy necessary to lift that 1 ton weight straight back up to its starting height. Now, the first positivity video explains how that aspect works in greater detail. I don't want to be too redundant. But in this case, this being lifted up from here to here is being lifted up with pure energy of this inertia. And that's why the time factor is relevant. So anyway, in this example, the wheel gains energy as the weight descends, but then if that energy is not immediately harvested from the center of the wheel in the form of electricity, when the weight is at its lowest point, then the wheel will lose that extra energy as the weight ascends up the other side. If this is left as a frictionless pendulum, energy is created on the downswing, and then energy is lost on the upswing for the first couple cycles. Yes, it is. So here's an old idea that would work if someone was to spend millions making this silly thing. This is a very lightweight rod with equal weights attached to both ends. The weight extending beyond the edge will cause this to spin as the weight descends. So it started up here and it's spinning that way. But then the inertia of this huge steel donut will keep this wheel spinning, pushing this rod back up, and the cycle will begin again. Yes, it will. This will work if someone was to do it. I drew this like this just for simplicity. The imbalanced weights could be designed so as not to interfere with the motion of the wheel, and so forth. So there would be one on each side to maintain perfect balance. Everything is perfectly round, blah, 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 as money can buy. Now, oh yeah, this is a solid steel donut riding along this rail on that axle. One rail on each side, which are designed to be frictionless using opposing magnetic forces. This central axle right there will be coming straight out this way, about 1 foot, toward this rail, which is also 1 foot out from the wheel. Same on the other side. So this is the end of the axle extending out from the center of the wheel. It rides along this rail, never touching because the opposing magnetic forces. And there's a lot more to talk about, but this is just for simplicity. And the same on the other side. So this axle is as thin as possible, maybe a 1/4 inch in diameter, to further reduce friction, etc. Lots of details that can easily be resolved. I'm not going to go into all that nonsense now. So this is a flat, level steel floor. Pretend it's perfectly level, no matter how it looks on your computer. Everything made as perfect as possible, etc. Now there would be a sweet spot for all this. Finding the correct length of the lightweight rod, the correct weight of these ends, the correct ratios, the correct size of the wheel, the correct weight of the donut, all that stuff. And of course we'll assume this is all in a giant room with all the air removed so there's no friction. So we set the wheel so that this weight is straight up, give it a slight push, and the imbalanced weights would slowly accelerate the inertia of the donut. As this reaches the floor, the inertia of the donut would in fact be enough to push the line back up. The wheel would keep rolling and the cycle would start again. If the floor and rail were a mile long, this would very slowly increase velocity for the entire mile, moving faster as the weight approaches the floor, then slower as the weight lifts up, as the wheel lifts up the weight, but still increasing velocity slightly with each cycle. And there are several variations of this same idea, all of which would work if somehow they were built. And all of this is assuming that the friction has been all but eliminated, And all these examples are simply to demonstrate that once friction is eliminated, as it is in empty space, right, the space between molecules, between stars, and so forth, once friction has been eliminated, all kinds of energy gaining over unity possibilities become available. Energy gaining over unity. So here's another version of the previous idea. We can assume this wheel is about 10 feet across, big lead donut around the outside. This big heavy wheel is being held in place by a stand, and the center is an axle which can spin inside a raceway at the top of that stand, but the stand is not drawn here, just to keep this simple. This wheel can spin around freely, perfect bearings, perfect balance, etc. This lightweight rod with weights at either end is off to the side, attached to this axle, which extends out this way a foot or so on each side. There is an identical one of these on the other side, and so on. Identical, perfectly balanced, blah, blah, blah. These weights are also, I don't know if you can see that. Whoops. Come back here. These weights are also perfect wheels which will spin freely when they roll along the top of this stand, which is underneath where these are going to be. So obviously this imbalanced weight will cause this to rotate, beginning slow, then increasing velocity as it descends. Here it has increased velocity at this point. It's getting closer and closer to the stand. When it reaches about here or so, the weight, which is also a wheel, will roll along the top of this stand, which will push this thing up to its starting position, and the cycle will begin again. So, oh yeah, these represent very small, lightweight pins very close to the axle, which will hold this thing in place as the wheel rotates. There's a million ways to do that. Now, the most efficient design for this type of wheel would incorporate the center axle itself, lifting this back into place. That's in the first positivity video. Whoops, sorry about that. So now we move into a different aspect of all this. Here is a lever, say 4 feet long, which can swing in circles around this axle. That's what that is right there. This is a lip, which is rigidly attached to this lever, so that if this lever is pulled that way, this lip will lift up this way. It is a solid steel L attached to this axle. This here is a steel rod. If this lever is pulled this way and this lip moves up this way, this rod will also move straight up, being pushed by the lip. We know that the force pushing on this lip will be much greater than the force pulling on this lever because of the leverage of this distance against the top of the wheel. Whoops, wrong page. If you set 100 pounds on here, then grab this up here, it will be easy to pull this back and lift that 100 pounds. If you were to grab it down here and pull, it would be much more difficult. We know that whatever we gain in force down here, we also lose in distance, blah, blah, blah. We would need to pull this back a foot for this to lift less than an inch. And because of this, we are taught that there is no way to take advantage of this extra force to produce continuous motion. And this is true if we only use inert mechanical attachments to attempt this. And I don't know if I mentioned this, pulling back this way, lifting this lift up this way, and that'll push on this rod, and the force at the top of the rod will be exactly the same as this down here, regardless of how long that is, as long as it's solid enough. So, I love my great artwork. These wheels can spin freely on top of these rods. This is that lever again, the L lever. It can spin around in circles around this axis, big giant spinning. Okay, So this is three different conditions of the same assembly. The same assembly at three different points in time. I just didn't draw this in these other two things. So this assembly here just represents something that would hold this rod in place so it can only move up and down, and it would be attached to the floor. And these things would spin in circles and whatever. So when this top wheel passes over this bottom, just barely skimming the top of it, this lip pushes up on this rod, pushing on this wheel, pushing it straight up. The idea would be that as this bottom wheel moves straight up, it will push against this top wheel with great force because of the leverage. This would cause this to move this way, which would lift this up more, which would push on this more, and so on and so forth. The problem is that no matter how the length of the rods or the length of the lip or the sizes of the wheels is arranged, this top wheel will always move away from this bottom wheel before the bottom wheel can push on it sideways with any force. And in reverse, if it doesn't, then they'll just push on each other and stop. So you could think of gimmicks like allowing this top wheel here to slide down the lever, and it would be ratcheted so it can't slide back up, etc. But this still won't produce motion. An outside source would need to move this. Nothing can be done with inert mechanical attachments. However, are magnets inert? No, they absolutely are not. Magnets are active and energetic. Look up Ken Wheeler if you want to know about magnets. But unlike a wheel and unlike a spring, a magnet is doing something even when it just sits there. It's doing something. And this activity can be used to take advantage of the extra force of a lever in spite of the distance problem. So you could loosely compare a magnet with a hollow pipe, that's what this is supposed to be, that has a very powerful motor inside it which sucks air in from this end and blows it out the other. If you put two of these pipes close to each other, end to end, depending on which ends you place near each other, the pipes will either attract each other or repel each other. Not exactly like magnets, this is just a comparison. So if we place two of our pipes, so this is just a representative, I don't know, this lip probably overlap a little bit too much. If we place, this is our pipe and this is another pipe, this pipe is sucking air through here and blowing it out that way. This top one is sucking air through here and blowing it out that way. There's an internal motor with its own internal battery doing this. Okay, so we place our two pipes so that as soon as this lifts up and this begins moving away, they will both be blowing each other in opposite directions. And if you coordinate everything correctly, this absolutely would work. And we would correctly conclude that the motors inside the pipes, which are blowing all that air, are actually powering this machine. So magnets push on each other in much the same way, but their internal motor requires no battery. So now, this gets a little bit complicated, I guess, I don't know. We will decide that these two rectangles are magnets rather than pipes. Two magnets at the top of these rods. But these shapes are not the shapes of the actual magnets. These are the shapes of the magnet's lines of force. These are the shapes of how these magnets will affect each other. We will shape the actual magnets, using a grinder in a machine shop, so that they will produce the correct shape of the lines of force, so that this top magnet will just barely interact with this bottom one as it passes over. But then, as soon as this lip lifts up this bottom magnet, the two will begin pushing on each other with significant force. And yes, that can be done. There's something called a Hallback array. There's a lot of ways to do this. The only direction allowed by this design is this way, counterclockwise. I don't know why I did that. So that is the way this will move. That pushing action will propel the top magnet momentarily. So for convenience, I will use this diamond shape to represent the actual physical magnet, stipulating that the lines of force are approximately as shown. These are the lines of force. Two of these are going to affect each other in this way, not in this way. Now I don't know what the actual shapes of the actual magnets would be. That would need to be discovered through trial and error, or I suppose a good computer simulation, but it would be close to, similar to this diamond shape. So, again, I've exaggerated all the distances to make this clear, to make it understandable. This thing would rotate in circles. Again, I drew it counterclockwise. Huge circles. There's the axle right there. Here's a lip that pushes up on this. This arm here swings up and down, so that can go up and down like that, blah, blah, blah. This thing would rotate in circles this way, and when it passes over this bottom magnet, this lip would push that straight up, and for a brief moment, the two magnets would push each other in opposite directions. The lip would then move past this rod, at the same time that the two magnets are no longer affecting each other. It would be designed that way, and the rod will fall back into its starting position. This would continue to spin because of inertia. We could have this attached to our perfect flywheel. So one gimmick I thought of, the magnets might tilt slightly as this approaches, and then both straighten up as the top magnet moves into place above the bottom, so that they could stay as close to each other as possible without pushing or pulling as this approaches this. It would take almost no energy to tilt the magnets when they are not yet affecting each other magnetically. So through trial and error and thought and everything else, every advantage would be utilized and every disadvantage minimized. The lengths of the rods, the lengths of the lip, the sizes and shapes of the magnets, and so on would all be coordinated for maximum advantage, and the machine would in fact run on the energy of the magnets themselves. Yes, it would. Yes, it will. If we have this attached to our superconducting flywheel, then each time the two magnets push each other, listen to this, the inertia of the flywheel will delay the time it takes for them to move apart. That delay will be the force of the magnets adding energy to the flywheel, exactly as our rockets or bowling balls did in the previous example. Okay, now this, of course, could also be expanded to have propulsion at both ends of a common axle. How am I going to point and read at the same time? In this case, this here thing would be one separate piece that spins on its own axle, and this here would be a separate assembly which pivots on its own axle each time the outer magnets pass over the inner magnets. In this case, this assembly would be counterweighted just enough so that the inner magnets return to their starting positions after they have pushed away the outer magnets. So it wouldn't matter how much they weigh. Okay, oops, here we go. This is a close-up of a possible axle arrangement that would serve this purpose. Okay, so this inner axle would spin in its own raceways, located at both ends of the axle, or maybe one in the middle, however many it would require. I'll explain why it's so long in a minute. And you can see, hopefully, that this is bolted to the floor. So this is holding a raceway. This thing spins inside it. Now this piece, Rachia, the outer of these two, well, okay, the bigger of these two, the wider of these two, that's what I meant. It's inside, but it's wider. Okay, this would be around the inner axle, but not touching it at all, and it would also be bolted to the floor. So this is a stationary piece, And that would be the raceway for this out. Oh, this is a stationary piece, and that would be the raceway for this outer piece, which would pivot back and forth. The bearings would be between this outside of the second piece and the inside of the third piece, right? 1, 2, 3. Okay, this dot represents a cam, which would be a small wheel attached to the inner axle that will push against this nub right there, causing this to pivot momentarily when the outer magnets push over the inner magnets, or push against the inner magnets, causing them to magnetically push on each other momentarily. I did not draw the magnets and the rods and stuff because I could not make it look right. The idea is that this single piece here, containing the outer magnets, which rotates in circles, oh, this is clockwise this time, is rigidly attached to this inner axle, which rotates in circles. Okay. Now this is a side view of the axle. This round dot is a front view of the same axle. Okay, so this single assembly right there is attached to, there we have big fun, this outer pivot. One arm coming out this way towards you, one arm going the other way. Whenever the outer magnets spinning on this inner axle pass over the inner magnets attached to this piece that can pivot, this cam causes the inner magnet assembly to pivot momentarily in sync with the momentary pushing action of the opposing outer and inner magnets. So seeing this from the front, when this pivots, let me get two different things here. This way, right, this is going to pivot, pushing this up, pushing this down. Causing them to push on the outer magnets momentarily as those outer magnets pass by. Also, as with many of these examples, this could also be made three-dimensional. That is why the axle is so long. Oh, a central axle going this way, whoops, a central axle going this way could be several feet long with 100 sets of these, far enough apart so they don't affect each other magnetically. These inner magnets, which move up and down, would all remain vertical. Oh, where am I? Still supposed to be on this one. Are we having fun? So these inner magnets, which just move up and down, would all remain vertical. Identical assemblies all in a row, including the attachments keeping them up straight, which are attached to the floor. And these rotating magnets that are rigidly attached to the axle would be next to and interacting with their respective partners, but offset from each other 1/100th of a rotation, if there's 100 of them on there. So there would be 100 of these sets, evenly spaced apart, each containing one pivot assembly. Next to each of these would be one rod containing the outer magnets rigidly attached to the axle, but each of those would be 1/100th of a rotation offset from the other. Okay, sorry about all that. So the law of conservation of energy has nothing to do with this because the magnets themselves are powering this device, just as our air-blowing pipes would, if we use them in place of magnets. Each pipe would have an internal battery to power the internal fan, and that battery would run out of juice very quickly. Our magnets will not run out of juice for many, many years, and when they do, much less energy will be required to remagnetize them than the total energy they produce throughout those years. That is a whole nother video. Now this machine may be the one I actually build, but it seems like it would be the least expensive design. Wouldn't need a perfect flywheel, and I wouldn't need 100 sets, maybe just 10 would do it. Okay, we're almost to the end. So sometimes I forget that most folks don't spend as much time and imagination on this stuff as I do, and don't easily see how these basic ideas can be expanded. For instance, this basic idea, explained in the first theory of positivity video, can be expanded in many different ways. So these rods right here will not lose any power if they are much longer than this. If this rod is 10 feet long, being pushed directly from the center of the axle, then the end of the rod will be pushing with exactly the same force as the center of the axle. Doesn't matter how long this is, it's simply transferring the power from the center of the axle to the end of this rod. So these could be two ends of two different magnets, say 10 feet apart, both ends acting simultaneously. And of course we could also have 100 sets of these on an axle several feet long, each offset 1/100th of a rotation apart, and so on, or just 10. In that case, we would use our superconducting flywheel at each end of the assembly, and maybe one in the center, depending on how many of these we have. So, I still think my best energy idea was one that I got when I was a kid, when I learned that glass is made out of sand. Build a glass factory in the desert, make thousands of giant magnifying glasses, use them to heat water to steam, and use that steam to turn generators to make electricity, turbines. A few years back I learned about a design by a Dr. Fisher, that's all I know about him, which instead of using steam, he would fill a closed container with water, heat it to 700 degrees, then spit that 700 degree water into a piston through an injector. The water immediately expands to steam with tremendous force and pushes the piston. Much more efficient than creating steam inside a huge container. So Dennis Lee and Dr. Fisher produced an amazing motor propelled by circulating refrigerant, which used no fuel at all. Dennis Lee went to jail, and suddenly refrigerants were blamed for the ozone hole. However, everyone educated knows that the atmospheric testing of nukes screwed up the atmosphere much more than refrigerants ever did. So look these guys up on YouTube while you still can, Dennis Lee and Dr. Fisher. It would be very easy to heat water to 700 degrees in a desert using giant magnifying glasses to run huge generators powered by Dr. Fisher's motors. There are hundreds, if not thousands, of other great ideas out there for producing clean energy, but they are all being suppressed. Why? The politics and psychology and economics of all this are explored deeply in the third Theory of Positivity video, which I'll be making next week. That video has no machines, it is all words, but very informative and uplifting. It is not about having a positive attitude, living in a universe where everything adds up to zero. It is about why and how the positive is equal to negative ideology persists in spite of the fact that it is so destructive and inaccurate. Positive is greater than negative. And not only that, positivity accumulates over time as negativity remains more or less constant. That may not be your life. It certainly hasn't been mine. But that is how nature works. That is how evolution works. That is, in fact, how physics works. Find out all the answers in my other videos. Okay, that's the end of this. I hope you enjoyed it. Please like and share and subscribe. That's what I'm supposed to say. Please like and please subscribe. Thank you very much.